Welcome to the Advanced SPARQL Queries session. Previously, you must have explored about RDF, SPARQL, and the basics of SPARQL. Now in this section, we will cover the advanced features of SPARQL. SPARQL is an acronym for SPARQL Protocol and RDF Querying Language. Thus, it is a graph querying language. So if your question can be translated to a graph pattern, then you can write a SPARQL query corresponding to your question. By graph pattern, we mean a set of triples that represents your question, which can then be evaluated by the triple store. Note that there can be more than one way to form a SPARQL query. Quite often, the right query is the one that retrieves results and it is fast in its execution. And the performance of your query depends on the structure of the graph pattern itself. That is, the order of the triples in the graph pattern matters. Now SPARQL has several features, and following are some of the features from the SPARQL 1.1 specification. We have negation, where you can define what you would like to exclude from your query and query results. We have property paths, where you can define a query that spans graph paths of arbitrary length. We have aggregation, where you can aggregate and compute on results based on some criteria. We have optional, where you can define optional parts of a query to ensure that you get results even if there is no matching data. We have nested queries, where you can define a query within another query. We have inference, where you can leverage the power of W3C standards and build clever queries. Named graphs, where you can query only data that belongs to one or more named graphs. And then we have SPARQL Federation, where you can query a local and a remote SPARQL endpoint together in a single query. Now we will look at each of these features in the next section. SPARQL provides the ability to filter certain triples from your query. The keyword that you would use is the filter keyword. Now let's take a look at an example query. Now this query has four parts: the prefix declaration, the type of query, the graph pattern of the query, and then finally the query modifiers. Most of the SPARQL queries we see in this session will follow this structure. Now the query itself is getting all instances of SPHN diagnosis, patients linked to this diagnosis, and optionally the age of the patient at the time of diagnosis. In addition, we are using the filter keyword to filter for certain sets of results. Here we are filtering for results where the age variable is not bound. That means we are getting all instances of diagnosis for which there is no information about the age of diagnosis. And we see that we are getting a distinct list of patients to avoid duplicates, since a single patient can have more than one diagnosis associated to them. Now here we see three sections. On the top left we have the same query from the previous slide. The RDF data that the query is meant for is at the bottom, and the query results that we get when we run this query against this RDF data is on the right. Note that this is a simple example for the sake of demonstration. In reality, you will be working with large-scale RDF data with the possibility of fetching larger sets of results. The RDF data is basically two instances of SPHN diagnosis, each linked to a patient, but only one has the age of diagnosis, but the other does not. When we run the SPARQL query against this data, we will get only patient 2, since the diagnosis associated with the patient does not have the age. In this way, you can make use of SPARQL negation to identify missing data points. SPARQL also provides another way of expressing negation. That is using the filter and the not exists keywords. As before, we are querying for all instances of SPHN diagnosis, patients linked to this diagnosis, and filtering the results where the age of the patients at the time of diagnosis is not available. And here we are doing that by defining a triple pattern within the filter not exists block. Now here we see the same query from the previous slide on the top and the RDF data at the bottom, and the results that the query would fetch against this data is on the right. This query would also return patient 2 because the diagnosis associated with patient 2 does not have the age information. So there are more than one ways to define negation in SPARQL, and how this negation is evaluated and run matters, and I think that will have an effect on the end result of your query. So you do need to be aware of what is it that you're asking for from the data when you're writing this query and making use of these keywords for negation. Next, we have property paths. As we're talking about graphs that contains nodes and edges, there are scenarios where the data points you want to get is either one hop, two hop, or several hops away. And by hop, we mean that you have to take one or more nodes in a path, and then you have to jump from one node to another and do this several times to get to your destination node in a graph. In SPARQL, you can express such hops as property paths, where you traverse through one or more properties to reach from one node of a graph to another node in a graph. And they don't have to be directly connected to one another. So far, we have seen queries with just one hop, that is, the property path length was just 1. But SPARQL allows you to express property paths of arbitrary lengths. On the right, we see 3 nodes, A, B, and C. If we want to go from node A to node C, you would express this as a property path in your SPARQL query, where you're not worried about the intermediate node, B, but rather only concerned with fetching the data points associated to either node A and or node C. Here's a more contextual example. Let's assume we have a lab test event node, which links to a lab test node. And then finally, we have a lab result node. And the properties that link the lab test event to the lab test is have lab test, and the property that links lab test to lab result is has result. And if we want to go from lab test event to lab result, then you would use a property path where you would express the properties in sequence. For example, here we would say the path is has lab test and then has result, and then you would use a slash operator to indicate that you want to query along this path, and the order of the properties in this path matters. So here, if you look at the SPARQL query, what we're doing is we're fetching for all instances of SPHN lab test event, and then traversing the has lab test has result property path to get the result in the end. So we're going from, again, node A to node C without worrying about the intermediate node, in this case, the lab test. Now on the top left, we have the same query from the previous slide, the RDF data that the query is meant for at the bottom, and then the results that will be fetched by this query on the right. As you can see, an instance of lab test event which links to an instance of lab test, which in turn links to a lab result. This is what we see in the RDF data. And in the query above, we're interested in getting the event and the result while skipping the intermediate node, that is a lab test instance. And so you can see that in the result, where you have 2 columns, one for event, the other for result. Property paths are a clever way of traversing and querying for specific parts of a graph. But you do need to be aware of the graph schema so that you're able to write property path queries. SPARQL provides various syntax to use with property paths. Previously, we saw the slash operator, which is used to indicate a forward path from a subject node to the object node. But there are also other syntax that we can use. There is the caret syntax, which indicates a backward path from the object node to the subject node. There is the pipe syntax that can be used to indicate where the forward path can be from a subject node or to an object node via one or the other paths. The star syntax indicates 0 or more paths between the subject and the object node. This is useful for traversing arbitrary path lengths. The plus syntax indicates 1 or more paths between the subject and the object node. This is also useful for traversing arbitrary path lengths, and this sort of makes the assumption that the path already exists before you can traverse down that particular property path. Now, the next feature of SPARQL is aggregation. SPARQL provides the ability to run certain operations on results fetched from a query. SPARQL 1.1 supports count, sum, min, max, average, group concatenation, and sample. One thing to note is that for most of the aggregation operations, you must also use the group by clause in your query. Now, for the sake of an example, we will look at the min-max aggregation in SPARQL. The query we see here is to fetch all instances of type blood pressure and get the corresponding value for diastolic blood pressure. After which, we apply the min operation to the value and bind it to the min variable, and apply the max operation to the value and bind it to the max variable. So the final result would be a table with the min-max values of diastolic pressure. Here on the top left, we have the same query from the previous slide and the RDF data that the query is meant for at the bottom. And the query results fetched by the query is on the right. If you look at the data, we see two instances of blood pressure where one has a diastolic pressure of 61 and another has a diastolic pressure of 132. The SPARQL query fetches all the values and then gets the min and max, which is the output as displayed on the right. And because we only have 2 data points, it seems simplistic, but this is typically useful for identifying outliers in your data, especially with numerical values, to see if there's something strange in your data. So far, we've seen queries where you get results only when there is a match for all the patterns provided in the graph pattern, that is within the where clause. SPARQL also provides an optional keyword that lets you define graph patterns that are optional. This lets you get results even if the pattern defined in the optional clause does not match any triple in the graph. This is often useful when you want to get all the results even when certain triple patterns do not exist. Here's an example of a SPARQL query that uses the optional clause. Here we are getting all instances of blood pressure measurement, the patient linked to this measurement, the result linked to the measurement, and then optionally getting the systolic pressure values and optionally getting the diastolic pressure values from the result. Here on the top left, we have the same query from the previous slide, the RDF data that the query is meant for in the bottom, and the query result table on the right. The RDF data tells us that there are 2 blood pressure results, where one has only diastolic pressure values, whereas the other has only systolic pressure value. Of course, this is a very simple example, but just for the sake of demonstration. Since our query is asking for systolic pressure and diastolic pressure values within the optional clause, we would still get results as shown on the right. Note that the systolic blood pressure value is coming from blood pressure 2 instance, while the diastolic blood pressure value is coming from the blood pressure 1 instance. But just because some triple patterns do not match, these results are not excluded, and that's because of the triple patterns being defined within the optional clause. The next is nested queries. SPARQL provides support for nested queries or subqueries where you can embed a query inside another query. From a query evaluation standpoint, the inner query is evaluated and executed first before the outer query. This can be used to your advantage since the subqueries can be used to reduce the search space. With SPARQL, many a times you will notice certain queries to run much better when you rewrite them with subqueries or nested queries. Here's an example of a nested query where first we will look at the subquery. In the subquery, we are trying to get all the quantities whose value is greater than 30. And then the outer query is getting all instances of body mass index and associated patients for which the quantity value is greater than 30. And if we had a query which went the other way, where first we query for all instances of body mass index and then filter for values greater than 30, then the query might have been suboptimal, depending on just how many instances of body mass index there are. Here on the top left, we have the same query from the previous slide, and the RDF data that the query is meant for is the bottom. And the query results fetched by the query is on the right. If we look at the RDF data, there are two quantities, but one has a value greater than 30. This is what will be fetched by the inner query. Then the outer query gets the linked body mass index, that is body mass index 1, and the patient linked to the body mass index 1, which is patient 1. And in the result, we only see patient 1 with a BMI value of 32. As mentioned earlier, nested queries are a powerful way of optimizing your queries by reducing your search space and also making sure that you're querying only a sub part of the graph itself. Next, we have inference. One powerful feature of RDF and SPARQL is the ability to use inference. By inference, we mean deriving new triples from existing ones. This derivation is possible because of inference rules defined as part of a particular standard. Triple stores generally support multiple inference rules because they are aware of these standards. For example, RDF, RDFS, SCOS, OWL are some standards that can be used for inference. With no inference, your SPARQL queries are interacting with the data as it is. But with inference, you can query the data by taking into account the semantics of the data. The most commonly used inference rules are from the RDFS rule set. Let's take a look at a simple example. Here we have two sections, the schema graph and the data graph. The schema graph is where we define the schema and the semantics. Here we are saying that class C is a subclass of class B, and class B is a subclass of class A, and all three classes are of type RDFS class. Now in the data graph, in the bottom, we have three instances where instance 1 is of type class A, instance 2 is of type class B, and instance 3 is of type class C. Pretty simple so far. If we were to query the data graph to get the instances, we would use the query in the top left, where we're just getting all instances of type class A. And at the bottom we see the data graph as RDF triples. In the absence of inference, the SPARQL query will fetch results where the information is explicit. Here, instance 1 is of type class A and is explicitly defined in the data. Thus, the query would return instance 1 as a result. But let's take a step back and look at the graph again. There's a need to also take into account the transitive property of the RDFS subclass of statement. When an instance is of type class C, and class C is a subclass of class B, which in turn is a subclass of class A, then all instances of type C is also of type class B and also of type class A. This transitive nature of the RDFS subclass of statement can be considered as one of the rules within the RDFS rule set. And the derivation of the fact that instance 3 is also of type class B and also of type class A is inference. There is no explicit triples in the data graph that states that instance 3 is also of type class B and class A. But a triple store that supports RDFS rule set would be able to infer this implicit knowledge and would allow you to leverage this knowledge while querying your data. Looking at the previous SPARQL query, but this time with inference enabled, here the data graph still remains the same, but we see instance 1, instance 2, and instance 3 in the result. This is as a result of the RDFS rule set being applied to the triples in the data graph to infer the new triples. And the RDFS rule set is basically defining that if an instance is of type class C and class C is of child of class B, then the instance is also of type class B. And similarly, if an instance is of type class B and class B is a child of class A, then the instance is also of type class A. And if an instance is of type class C and class C is a child of class B and class B is a child of class A, then the instance is also of type class A. Of course, this is all written here for the sake of readability. In reality, the rules are defined in a much more abstract manner, but it is something that is understood by the triple store. And so there's nothing you have to supply except for the fact that you have to turn on inference when you're running your queries against a triple store. A more contextual example would be with leveraging class inheritance with SNOMED-CT. In SNOMED-CT, we have a diabetes mellitus disorder concept and two child concepts, diabetes mellitus type 1 and type 2. And our query is to get all diagnoses coded to diabetes mellitus regardless of the type. Now here the query on the top left gets a diagnosis, the patient associated to the diagnosis, and the code associated to the diagnosis. And we constrain the code to be the diabetes mellitus concept from SNOMED-CT. Below we see the RDF data where we have one diagnosis coded to diabetes mellitus type 1 and another coded to diabetes mellitus type 2. That is, no diagnosis is directly coded to the diabetes mellitus concept from SNOMED-CT, which is what is specified in the SPARQL query. If we were to run this query without inference, then we would get no result, since there are no explicit triples in the data. But with inference enabled, the triple store infers that diagnoses coded to diabetes mellitus type 1 and type 2 are also coded to diabetes mellitus. And we see that in the results where both the diagnoses are shown when the inference is enabled. And this information of diabetes mellitus type 1 and type 2 being subclass of the diabetes mellitus concept is already defined in the SNOMED-CT. And so your data would have to be present with the SNOMED-CT terminology for this inference to be possible. So inference is a powerful way of working with your data, especially when the semantics of your data is defined as part of a standard or a schema. Another feature of SPARQL is named graphs. SPARQL provides the ability to organize your triples into collections. A named graph is a collection of triples that has been assigned a unique URI, or rather a name. Named graphs allow you to organize triples in your graph based on some criteria. For example, you can organize your triples into one named graph per patient or one named graph per data provider. And at query time, you can specify in your SPARQL query which named graph you want to query. Alternatively, if you want to query all the named graphs, then you just have to query the default graph, where the default graph is the combination of triples from all the named graphs. Here we see a simple SPARQL query to get all instances of RDFS class and labels from a named graph. And the named graph here is basically a graph that contains the unified codes for units of measurements, or UCUM codes. And the query will get only triples from the UCUM named graph. Queries to the named graph can often be faster than those to the default graph, since you are querying for a small subset of triples as identified by the named graph URI. And named graph are also a useful way of updating or deleting parts of your data from a graph. Because you can refer to them as a collection using the named graph URI, it is easier to manage them. One interesting feature of a SPARQL is federated queries. A federated query is where you combine two or more SPARQL endpoints within the same query. In your SPARQL query, you can define the endpoint to use using the service clause, and you can define multiple endpoints within a single query. One thing to note is that the performance of your SPARQL query will depend on the responsiveness of all the endpoints involved. Here's a small example of a federated query. First, we are querying for all instances of RDFS class and getting their labels within our local default graph. Then we are querying for a remote SPARQL endpoint as identified by the URI example.org/SPARQL, and then getting alternate labels for the instances. Ideally, the query would then return results where you have all instances of RDFS class, its label, and then the alternate labels from the remote SPARQL endpoint. Now, of course, this is a very simple example here, and the remote endpoint here does not really exist, but this is just to show the syntax that you would use for federation. Federated queries are a powerful way of combining data from multiple triple stores to get an enriched set of results. But keep a few things in mind. The nature of your query depends on how clearly defined the schema of all the SPARQL endpoints are, because you have to be aware of what you're querying before you can query. And the success of the query depends on how responsive all the SPARQL endpoints are. So just one thing to keep in mind when trying SPARQL federation in a real-world scenario. To learn more about SPARQL 1.1, we would recommend looking at the W3C SPARQL 1.1 specification. And to do more about federated queries, we would recommend looking at the W3C specification on SPARQL 1.1 federated queries.
We will now present some best practices that can be followed when writing SPARQL queries. Please keep in mind that SPARQL is a standard querying language, but some triple stores that you can use to query for data with SPARQL may have different interpretations of the same SPARQL query because they may process it differently. You must, however, get the same results in each triple store you use for the same query, given that you apply or have the same settings, for instance, when it comes to inference. However, the tips and tricks we present here are generic and would likely work on most triple stores. In general, it is important to know how the schema is defined. This helps in assessing how the data is formatted and therefore helps in writing the queries correctly. In addition, in the case of SPHN, since value sets can be coded with external terminologies, it is also good to have an idea about how they are structured and which values or codes are of interest. And above all, make sure to use the right version of these terminologies because the data can be coded with different versions. When building your query, organize it as follows. First, declare your prefixes. That way you have abbreviated and shorter namespaces. They will help you to have more readable queries. Write descriptive variable names. Don't use, for instance, single letters for a variable. If you're looking for a patient, really write ?patient to bound patients to this variable. Then structure a graph pattern in a logical manner inside the where clause. You can, for instance, define the type of your variable. Is your patient a subject pseudo-identifier? Then connect your variables together and filter as needed. Finally, comment your query. It is never helpful to have many lines written without context or information about what they do, and it is even sometimes difficult to understand what they do, so commenting can be insightful and help you remember your intent at the time of writing the query. When going through the creation of a graph pattern, we encourage you to apply for a sort of funnel thinking, where you would filter for the most selective items on top of your graph, so it gets processed first and removes as many instances that are not compliant or fitting to that selection. This will allow you to focus on a lesser amount of elements in the graph than what you initially had, which basically contained all the triples in your knowledge graph, and that may be a huge amount. And this is especially true based on the assumption that most triple stores will process the graph pattern from the top to the bottom. Of course, if you're using nested graph patterns with the subqueries, then the inner patterns would be processed first. So we advise that you put the most selective items in the innermost graph pattern. When writing queries in SPHN, we can recommend you to apply the following methodology. First, describe what you want to do and retrieve as a result. Here, I want to get all male patients with a BMI above 30. Then look at the schema and check how the different concepts or classes are structured in order to know how to query for the specific data instances you need. Make sure to also have a look at the codes being used. Here, for instance, the administrative sex points to a code, which is a SNOMED-CT code that would either represent male, female, or other as possible options. And the body mass index, for example, here is linked to a quantity, which most likely would contain the value of interest for the BMI. In the next step, we will divide the question in two. On one side, we will focus on patients being male, and on the other side, we'll have BMI above 30. So we start writing the first filter. Here, we want to get all patients, which are male patients. So you can see that we have in our select statement two variables of interest, the administrative sex and the subject pseudo-identifier. In our where clause statement, we define our variable administrative sex to be of type SPHN administrative sex. It must point to a code which is this SNOMED-CT code corresponding to male patient. And finally, we want to bind this administrative sex variable to a subject pseudo-identifier, which would be our patient of interest. Similarly, we'll do the filter for the BMI above 30. So we are retrieving all patients with a BMI above 30. And the following pattern is applied. So we have a BMI instance, which is a body mass index. It connects to a particular patient. The BMI has a quantity, which we define in a separate variable. And this quantity has a specific value, which we filter to be above 30. Then we combine the two queries that we have written previously, and we make sure to add the variables of interest in the select clause. You can run your query and check for the results. You can, for instance, pick an instance of one of the subject pseudo-identifiers that you retrieve and explore the related data to make sure that the results make sense, that it is indeed a male patient which has a BMI above 30 in this case. Some triple stores actually have a nice user interface that enables you to dynamically navigate through the different instances of the data elements that are connected together. You can also always improve the output. In our example query, we have as an output the actual value of the BMI, but for the administrative sex, we are only giving as an output the instance of the administrative sex. You may want to actually add a variable to retrieve the actual code and being displayed in the output. Finally, if you feel like your query is not fast enough or is hanging without giving you results, you can try to write an explain statement to see how your triple store seem to run the query and adjust your graph pattern accordingly by moving some of the lines or rewriting some of the statements. Now let's see some of the common pitfalls that are observed and that you could think about when your query is either slow or not retrieving results as you would need. The variable binding are maybe not matching. So in this example, the query retrieves pairs of resources and their associated values for two different properties. So this will give you actually all the possible permutations of the pairs, since there's also no relationship specified between the different values of A and B. We would like you to be careful about case sensitivity. So if you ignore it, your query most likely will not find data that matches. This brings us back to the point that it is important to know about the schema and really check how the classes and properties are written. In this example, the reference range actually has a lowercase r for the range, while it should be an uppercase r according to the specifications of SPHN. Then keep in mind that every line that you write in your query is actually a filter, unless you state it as an optional. Here you're checking for instances of reference range where you're asking for their upper limit. So you are excluding the reference ranges that do not have an upper limit, and they will not be retrieved in the result. However, you also have an optional statement that retrieves the reference ranges that have a lower limit, but this is not an exclusion criteria. So in case you have an instance of a reference range that does not have a lower limit, you would still have it as a result. But be careful, in the optional statements, all the lines provided must be met in order to retrieve that optional in the result. So in this example, you define 4 triples. All of them must be true so that the values are present and displayed. Otherwise, if at least one of them is missing, the result will provide all these variables as blank. So generally, you should not include all optional triples into one single optional statement, but rather define them in individual ones, unless you have a valid use case, of course. When you run into issues with your queries, either not retrieving the possibly expected results or the query never ends, you can try to debug it by running each line of your query individually and gradually adding additional lines. See the results provided and see if they make sense. Always try to cross-check the results as we explained to you earlier. So when checking for patients having a BMI above a certain value and patients having a certain administrative sex, we first did a filter on the BMI only, for instance, take a note of a few of these subject pseudo-identifiers that were retrieved. Then we check for the administrative sex for them in the interface, for instance, and we could then continue building the query for having the actual statements we need or the actual results we need. Now, when it comes to performance, we would like you to keep in mind that you should not expect the same level of optimization than on traditional databases because of the complexity of the data. The difference also that we have between the SPARQL query language and other relational databases. So SPARQL query or graph triple store queries are usually designed for handling complex graph traversal or pattern matching, for instance, which is quite hard to optimize, while for relational databases, they are very efficient at doing other things like indexing and data aggregation, and these are highly optimized for these purposes. So when writing your query, you can make sure to use the SPARQL subqueries, as we mentioned before, where the innermost SPARQL statement would typically be evaluated first. So we recommend that you put the statements that will ideally reduce the search space in the innermost SPARQL statement. Again, use the explain statement to see how your triple store is processing your query, and then you can eventually adapt your query as needed to make it faster. It is also important to know the cardinality of your data. That helps you to assess if you can actually get some information or not about a particular subject or statement. And sometimes you may realize that explicitly binding your variables will work like a charm, meaning explicitly specifying the actual value of a certain variable in your SPARQL query, if you can, of course. That can significantly improve your query performance and efficiency. We will now see 2 examples of queries which are actually retrieving the same result but are written differently, and therefore they may be processed or are most likely processed differently by the triple stores and have different performances. So in the first query, we applied this top-down approach. We are interested here in a specific drug administration event where the substances given to a patient are of 2 different kinds, highlighted here with those ATC codes. So this first query basically defines first the drug administration event and then narrowing down the path to the specific codes we are interested in. So we define our variable of the drug administration event to be bound to a subject pseudo-identifier, therefore our patient. This drug administration event is of type drug administration event. The variable should be bound through a drug to an active ingredient, which is a specific substance that we are interested in, and this substance must be of these specific codes. In the second query, we applied this funnel approach we presented before, where we would like to basically eliminate as much as possible of triples or data elements that are not of interest for us. So for that, we use a nested query in this case, where we select for the substances of interest, and we assume that this would basically eliminate most of the triples, and then we bind this substance to a specific drug administration event following this path, and we specify this drug admin to be of type drug administration event and be bound to a patient. So in this case, we can assume that the query might be faster than in how the query was built with the query 1, in case the substances which have these codes are not so many, because then you would only focus on these substances and then you can connect the other pieces of information that are directly relevant to it. While in the first query, you really had to dig through a whole lot of possible drug administration events, and then actually inquire for the actual substance that you are interested in. So we could assume that the query 2 might be faster, but this of course depends on your data. This depends on the triple store you're using and how they're processing the query. You'll find some references here to read more about SPARQL, and a nice platform where you can test and learn in a more hands-on way about SPARQL queries. Thank you for your attention.